People of the Polish community who may be here, people from the Royal Aeronautical Society, and our own students within DIT. Today I have the pleasure of introducing Professor Wiesław Binienda. I'll get it right. I'm still trying it for the last while, but I'll get it right. From the University of Akron, okay, in Ohio. And he has come here under the invite of the Polish discussion group in Ireland and the Royal Aeronautical Society, and with the help of DIT, to discuss the characterization and modelling of aerospace materials and structures. The professor himself is director of the Gas Turbine Research and Testing Laboratory in the university, and also chief editor of the Journal of Aerospace Engineering. Among many of his accolades is NASA Prize for Turning Goals into Reality Award for his research, and also he's had numerous other accolades, which he could probably tell you more about than I could. But basically what we will do is, in normal operations here, we'll let the professor get on to his lecture, and after the lecture we'll have a quick question and answer session for everybody. So without any further ado, I'd like to welcome the professor here. Thank you.
Well, thank you, Paul, and thank you all Irish people for inviting me here to Dublin. I had a chance yesterday, the day before, to try your beer. I have to say, very good. The weather is iffy, you know, it's every day something else, so I know that this is not the best in January or February to come here to Ireland, but I heard that summer is much better. In my presentation today, I'm going to present kind of two parts. The first part will be fundamental research that we conducted recently, and later on it will be applied, this methodology, to a particular problem. The problem that the methodology is going to be applied is to be a crash of the aircraft that I will discuss in the second half of my presentation. In terms of advanced materials, everybody knows that original materials that are still flying in our aircrafts are aluminum alloys. But recently, more and more, they are replaced by composite materials. So, in our group, we decided to try to understand and develop technology for braided composite materials with the graphite fibers. And you can see on the right the big braider and effect of the braider that is used to produce the containment system for the jet engine. We started this work in 2000, and over the time we developed a very strong material. I have a sample here, so if anybody would like to come and see how light it is and how strong it is, you are welcome. Basically, the idea is that the outside section of the jet engine, the front part of the fan, has to be protected by a cylinder-shaped structure that is capable to withstand impact of the blade if it is released at the maximum RPM of the jet engine. This is required by FAA, and you can see here the test that every jet engine it has to pass. It is called blade out test for the jet engine like the GE90. It costs more than $20 million. So if you can imagine the test that this is in particular Rolls-Royce engine and is conducted in England, this test, but the same test is done by other companies like GE or Honeywell or Pratt & Whitney and other companies. So the test, as you saw, was very quick. You know, it was just a millisecond. Of course, we use high-speed cameras that is videotaping that, but even with the high-speed cameras, we can only see a little bit of the action. It's very hard to measure, and I think because the energy involved in those tests. So you can imagine that basically the prototype of the engine, which is expensive in its own, is basically destroyed during this test. Now, as I mentioned, this is the required test for certification. So companies, they have to do it, but they don't like to do it too many of those tests, okay? Because if they can limit to one or two, they are very happy. If this test would not pass, of course, then they have a big trouble, because then they have to go back to the drawing boards and they have to continue making modification to the design and slowing down the process of delivering the product. It costs even more money. So what they do, they over-design. That is normal. And if they over-design, the engine is heavier, and we pay for that, all of us who are flying airplanes, because then the tickets are more expensive. So the idea was to replace the heaviest part of this engine, which is that containment system, by material that is much lighter, and this is what we succeeded by using this braided material. So we have started to develop technology from the material point of view, that we have to characterize, understand, be able to describe mathematically and physically through a system of tests, and then develop the fabrication process that will be automated, so that the system can be done again and again with the same quality. And here at the oops, okay. Here it's my laser is not working. Okay. So the one that I was trying to shine is the containment, as you can see. Okay, this one. So this is the containment system, and basically it's flying with the engine, and it's a dead weight until it's necessary to stop this fragment of the blade to penetrate the engine, and of course to protect the wing of the airplane or a fuselage of the airplane, and make possible, even in such situation that the blade is broken, for the airplane to land. In order to understand the whole system, we had to look into it from the material point of view, of the micro level, and meso level, and macro level, and also on the structural level. So this is the so-called multi-scale approach, and required to analyze and characterize the polymer itself that is used as a matrix in the composite, the composite itself as a micromechanical point, from the micromechanical point of view, then understand the architecture of the material, which is the mesomechanical level, then go into laminate, which is the micromechanical level, and make a structure, which is the structural level. We use different matrix materials and limited ourselves to 700 Torres T700S fiber, which is Japanese fiber. And you can see architecture, and again, the same architecture is seen here in the sample, which has 3 directions of the fiber. Is 0 embedded inside of these bundles, and plus minus 60 braided over and under through the system of braiding. So this, in mechanics of composite, we call it quasi-isotropic material. It means that from the point of view theory, it's supposed to have the same properties in axial direction, which is this one, as in transverse direction. Of course, when we test, you can see that at different level, we will focus on different mode of failure. We can see that the micromechanical level, the adhesive or cohesive fracture of the material itself. We can see from the sample level the tension results, which looks like shear, and from the structural level we can see the damage due to application of the internal pressure, which makes the crack driven by the structure geometry of cylindrical structure itself. So in order to characterize the resin material, we developed special small samples that we could get the results under tension, compression, and torsion for the shear. So we had a small cylinder, and we used a digital image correlation technique to observe the deformation of this material. I'm sure in your university you use digital image correlation widely. It used to be advanced method of measurement, but right now it's very common, so I'm not going to discuss that. The small tube is shown here is of course for the torsion, and below is empty inside, and the tube of that kind can be used for the static test as well for the Hopkinson bar test for the high rate strain rate. So you can see the results of the strain rate testing, that the higher the rate of deformation, the different stress-strain relationship you can get. And it is basically elastic and plastic material. You can get as high as 50% strain for the resin itself. Now, because of the viscoelastic properties, if you load and unload, you can get key hysteresis of this test, which means some of the energy would be absorbed through just loading and unloading. And all of that is important because we eventually have to develop the constitutive equation that would describe this behavior of the polymer composite that we use in this material application. So we use the modified definition of Drucker-Prager yield criterion for to account for hydrostatic stress effect, presenting the polymers and strain rate dependent elastic, and basically this is some mathematics that describe the stress strain using the compliance matrix and the functions that use in the constitutive equations. I'm not going to spend all the time, but basically this is quite simple for the constitutive equation system, but still has 7 parameters that need to be determined experimentally. And of course this is not finished. We also had to add some damage that is involved in the material itself as a matrix. So the damage is reducing the Young's modulus. You can see that the more the damage, the different slope, even at the beginning of the of the stress strain curve is obtained, and that need to be related mathematically, and it was captured using the damage parameter, which is basically defined using Kachanov type of definition. The revised model is described here by this equation, where you have effective strain and damage parameter involving in this equation, and therefore you can have the sensitivity to the behavior of the material, not just as a virgin material as it is new, but also when it is damaged. And we developed UMAT for LS-DYNA, which is basically a system of steps that will incorporate this model into the finite element calculations. And the bottom line is to have experimental data and simulations, and convince yourself that yes, you capture the behavior of this material at different strain rates, and you have it that you can use, you can move on to next step of the analysis. One addition to the behavior of the resin material is that it's unfortunately suffers aging during the lifetime application. So it means that when we produce the composite and we put it into airplane and it flies and changes temperature from temperature at the tarmac to the cruise temperature, which is very cold, and then lands maybe in Hawaii and it's very hot and humid, or in Dublin, which is also could be very humid. Then all these conditions and application of different gases can deteriorate the material behavior. So we were asked to use our laboratory, and we have special environmental chamber where we submitted this material to the aging process, and we tested again and again after months, 2 months, 1 year, 2 years, 3 years, 4 years, and find out if this material is going to behave properly at the end of life. Because the designer people, you know, it's easy to get the properties of the material when it is produced. You can go to the laboratory and test just after fabrication. But as a designer, you have to design the part, the structure, at the end of life, because it has to efficiently behave and do the job at the end of life, not at the beginning of life. So we found that indeed the aging is changing properties of resin from very elastic plastic to less plastic and to very brittle material. It changes also the color, as you can see through the cross-section of the broken specimen. So once you understand the limitation and behavior of the resin itself, then you can go and make a composite, and then you go and try to test the composite. Of course, from the testing point of view, there are ASTM standard tests. I don't know what test you use here in Ireland, but in the United States, ASTM is the way that we follow. Unfortunately, this is a coupon of the simple tensile test, and you can see that the edges, this outside edges, basically cuts through the bundles that are plus minus 60. And this has, we found, a consequence on the results of the tests. So we had to develop a new test outside of ASTM standard, and we were looking for first of all, to understand so-called edge effect, and you can see this edge effect in the DIC methodology. This is experiment that you can see the edge effect, which gives different stresses than they are inside. And of course, non-homogeneous stresses or strains visible, like you can see maybe a damage, local damage, split or fracture or debonding between fiber and matrix. All of that can be overlapped on the global strain, but locally they produce different stress-strain relationship, and they need to be known and somehow incorporate into constitutive equation later in the modeling. So we spent a number of years to understand the different failure modes. We found through the thickness, the splitting of the bundle that are shown circled, and we look at the microscope, we look at the bonding at the fiber level, and we found that even for the same fiber, but two different resin, which globally gives almost similar behavior, the local stress strain can reproduce different damage progression or behavior of the material itself. We attribute that to interface. Okay, we can have material with strong interface that is on the left, and with the weaker interface which is on the right. So although we combine materials that physically behave almost the same, but because of the interface the effect could be quite different. And again, a lot of tests that showing the mode of failure under tension, and this is pictures from the high-speed cameras that show how quickly, this is 40,000 frames per second, so within 12 frames of the 40,000 frames per second, you can see the damage progression. So you have to capture that very quickly, otherwise you don't see that at all. And then all these tests are put together in the mesomechanical model, which is shown here, and macromechanical model. For macromechanical model, we divided the braid, so-called representative volume element, to subsections A, B, C, D, and in subsection or subcell A and C, there are fibers in plus, minus, and 0 degrees orientation, and B and C are plus, minus 60 different orientation. For the mesomechanical model, the idea was to use solid elements. For macromechanical model was to use shell element, and of course shell element will lose some of the information that the solid element can provide, but for the structural analysis the shell element is the proper way to do it, not solid elements. So again, all the way of contributing this to the model with the cohesive element used to measure the strength of the interface. And of course, those people who understand fraction mechanics, you know mode 1, mode 2, mode 3, and they are all captured in cohesive element. And the bottom line is that you have then significant number of parameters you can adjust and make sure that the simulation, as you can see here, for the axial tension, transverse tension, axial compression, and transverse compression will capture the experiment as measured in the laboratory. And also you can look at into the analysis and try to understand if you capture not only the slope stress-strain relationship, but also you can capture the damage, and this is on the left simulation and on the right experiment, which really indeed captures those failures that occur in the material itself, and again for other tests are shown here. Same thing you do for macromechanical model, and eventually you can get the tests and samples that gives the good results. for the micromechanical tests. These are tons of tests, so I'm not going to spend too much time. We developed a modified tensile specimen which with the two slots here, and the idea is that those bundles that come through the gauge area of the test will be embedded in the rest of the material, therefore you will not lose and you will not create those edge effect, and therefore get better, closer results to the test. However, we found that this has a consequence of testing locally under biaxial loading conditions, not uniaxial, which makes also a big difference. And again, high-speed cameras with the 100 frames per second can give you the test. It slows down the process of damage because you have this embedded angle fibers, so therefore you can capture that as well pretty good. Well, the test that will eliminate any edge effect is of course cylindrical tests. So we develop a special machine, testing machine, that can put the specimen, which is a tube cylinder, and we can pull it, twist it, and apply internal pressure. This is 40,000 kips machine, very huge, and a company that is making the braided material, which is A&P Technologies from Cincinnati. They put a lot of effort to produce the multi-layer tubes, which is task by itself significant. And of course those tests are very expensive, but can produce results without any edge effect, therefore can be used to validate any other type of testing, which would be much simpler on the regular specimen. This is showing some video of making the gripping area, which we had to overlap with extra material and then machine it. So that takes a lot of time of preparation for each of the tube, and you can see now the test itself in the machine. You can see my graduate student sitting behind and controlling this process of testing. And pretty soon you can see two cameras that is measuring through DIC these spots that are painted on the surface of the specimen, and they will eventually post-analyze in the computer and show those fringes of the strains. And I'm just shaking hands with my camera, waiting for test results. And worrying that maybe if it explodes, because it may explode, then I will be full of shrapnels. But what we do for science, right? We devote our life and make sure that we can get results. In this case, it was safe because it debundled at the gripping area, so it didn't break, and the results are need to be repeated anyway later on. So in terms of static tests, this is the capabilities of our laboratory. We can do the STM standard test or non-standard test, but also we have the gas gun that you can see here, that we can test the material under the impact conditions. So that will give us the larger plate that is impacted under the let's see if I can. This is supposed to be a video, so here it is. So you can see the gelatin is splashing into the material, and we have to characterize the projectile. In this case, it is gelatin itself. Then we look at the gelatin looking from the DIC method, and then we can apply the DIC to the test itself. This is an interesting test because it will show how aluminum, the original material, will behave under the gelatin, which is so-called artificial bird. Well, here you are, it breaks through, and not only it breaks through, but rips over a huge hole. So aluminum is, as standard material, is very dangerous because yes, it is elastic plastic, but if it breaks, it can open a significant hole in the engine, and therefore those cracks are not arrested. And you can see on the left the deformation of the aluminum before it fails, a little bit more higher velocity, and it failed, and the failure is definitely very detrimental. Now, the composite offers more crack resistance, so when you have a failure, you have local fiber breakage, but even if you have a, let me see if that would show. Even if we have the application of this material, you can see it is more elastic, it is gentle, it behaves like a spring, and therefore saves itself. And it was interesting to me that the common sense would be that if you have thicker material, you have more protection. In fact, in composite, the thinner material, to a certain extent, gives you more protection because it's more elastic, and therefore the damage is not as strong, and that was analyzed through all this analysis. If it fails, of course, because you can always apply force that will fail, the damage is much more localized. It basically breaks and opens the gate, and the projectile flies through, and therefore the damage is not as bad as one would imagine. You have here the whole matrix of damage, and you can see that for the same fiber, just by changing the matrix, the so-called V50, which is the velocity of penetration, can be significantly different because due to the fact of interface strength. In fact, again, the common sense would tell us that the stronger interface, the better. In fact, in the impact, the weaker interface, the better, because the material starts to spread the forces through itself by evaporating or decomposing itself, and fibers are by pulling from the matrix and from the other fibers can absorb much more energy, therefore it can get much safer for the experiment that we use. This is the system of UMAT applied at the integration method, at the integration point, which basically take the behavior of the resin and failure using the micromechanical model, and these are the results of the simulation with respect to experiment, which are satisfactory for us. And again, you can see damage model using the so-called slice model that we use to incorporate and get the final results. Once we can get the results not only for the deformation, this is experiment, this is simulation, but also for the shape of failure, then we are very happy, and we can start to making changes to the orientation or architecture of the composite. And over here we have plus minus 60, and we have so-called butterfly shape of the damage. Here we change to plus minus 45, and completely different shape of the damage, and which was predicted first and then tested, and indeed it was confirmed that the damage is like that. Now the result of this is structural analysis, and then $20 million test can be done on a computer, which is free almost, because this is cost of graduate students, and you know how little we pay graduate students for their work. So it's indeed time of computers and simulations, and we can get more information from simulation than from the experiment, and therefore FAA is very happy, the aircraft companies and jet engine are very happy, because now they can make modification, they can come closer, they don't need to over-design the structure, and they can save more weight, and we were able to save 30% of the weight of the jet engine by using this technology in terms of composite materials, and also using our simulation method, which is a big success for a small jet engine company like Williams. They lost a contract for a small business like airplanes because 2 pounds overweight of the jet engines. Then they came to us, they use the same material for their jet engines, they save enough weight, and they are competitive again on the market. So by doing this, we can save and allow companies to compete and save billions of dollars in terms of production of the long-term work. Now, of course, aluminum is still very used material, so the FAA asked us, together with NASA and the other universities, to understand aluminum use for the aircraft, and we found that the failure of aluminum 2024 T351, this is errors, it should be 2024, not 14, can be described using triaxiality conditions, which is defined here, which is the pressure P defined using the principal stresses, and the von Mises stress, which is effective stress. So, of course, this can be all described using invariants, and again, I'm not going to put too much time for the mathematics, but I just want to point of view the triaxiality and so-called Lodi parameters. This one on Lodi angle, define this one using the J3 invariant is used to describe the behavior of the aluminum. So all the aluminum is isotropic, but we found that based on different triaxiality, it behaves at failure different way. And this can be shown by experiments under tension with grooves on the left 1, 2, 3 test or punch test. And of course that can be done using, similarly like for composite, using different strain rate. So what is interesting that we can see at 20C that under different rate conditions, the red is the fastest, that we can see that when the faster we apply load, the stronger the material is, and also not like in composite, the maximum strain is not deteriorated, which is very, very good for aluminum. Now also in the room, for the same strain rate but in different room temperature or low temperature especially, the low temperature is the blue minus 50C, which is the cruise temperature of the airplane in the 30,000 feet. Or room temperature, you can see that again when the colder the material is, the stronger it is, and still not losing any of the strength. And we can again observe experimentally, and we develop a special specimen. This is a special specimen that is a punch, and that punch expands the size of the specimen, at the same time pushing the bottom and therefore producing the three-dimensional state of stress at the bottom, tension in X and Y, and compression through the thickness. So this is the negative so-called Lodi parameter or Lodi angle and negative triaxiality. Now, all of these tests that are shown at the outside of this slide are needed to produce so-called failure envelope. So this is the failure surface that for aluminum that shows how dramatically different failure can be depending on the combination of the state of stress that you apply for this material. Once this material is characterized, it is put into LS-Dyna as a so-called tabulated model material 224, which means that the experiments are completely embedded in the numerical model. And we can see that we can capture the ballistic test for different thickness of the plate on the left and compare with the experiments on the right very accurately. Same thing for tests that are different than ballistic. And I use this material to find out how is it possible to find if it is brittle at higher velocity. So we use sabot, and this is our gas gun in our laboratory, and you can see the result of the impact when the sabot is accelerated in this tube and hit into the, impacted into a very thick wall. So this is like a rigid wall at speed of sound. So from this you can damage this aluminum completely to that part, but there is no any brittleness. The material basically is very plastic, and we can also capture that using material 225. So all of these tests will allow me now to go to the next step of my presentation, which basically would be applied all these material models, both aluminum and composite, and because wood is a composite material, so we can get the same. And at the beginning I just shown this is the new Gen X engine that was produced by GE that is used as one of the equipment in addition to Rolls-Royce for the Dreamliner. So, and of course it is available for other airplanes as well. Same material, of course, if it is good, is now designed and used for helicopter shaft, so in the future will be more applications. But let's go to the problem that I would like to apply my knowledge, my methodology that I described here, which basically is involving the crash of the Polish government airplane, which happened in April 10, 2010, where the President of Poland and many officials died. And I'm sure you heard about that. So, based on this methodology, which by the way was used also to analyze crash of shuttle Columbia before, and I knew that this would be good methodology to use to analyze some aspects of this crash. So I was waiting for the official report, and you can read from the official report here a statement in section 3169 that the aircraft collided with the birch tree with a trunk of diameter 30 to 40 centimeters, which led to the left outer wing portion of about, first they say 4.7, then they measured 6.5 meters long, ripped off an intensive lead bank. In 5-6 more seconds, inverted aircraft collided with the ground and was destroyed. We are talking on the aircraft Tupolev 154, which is similar to Boeing 727, which is about 40 meters wingspan and 50 meters long, about 100 tons of the airplane. So based on this reading, this is about 6 or 5 meters from the ground that was measured by the investigating committee, And they say that at this location of the birch, the airplane lost wing. And of course, when they lost wing, you anticipate the plane would lose some of the energy, right? Because they lost balance of the lift force, so it makes sense that it goes down. But somehow then they said, because of the black boxes, measured the height, that the airplane was able to go around, starting to go around without that wing. And at the location of this location, something happened, because this is the horizontal trajectory. By the way, this was supposed to be a real trajectory, but it was incorrectly directed by the ground navigation people, and they directed on wrong path. But anyway, something happened, because the plane that was flying straight turned left sharply, and at this location lost all the electric power. And that location, you can see, it is about 30 meters above the ground, and this is from the Russian report. So you think about this and say, it doesn't make sense that an airplane that is going down without wing, which makes sense, now is able to go up again, and you calculate, anybody can find that the airplane is flying 80 meters per second. You can see the distance in meters, so you can calculate what is the change of the velocity, and you find that in this location where you change the velocity from going down to going up, the g-force has to be about 10 g. So it is physically impossible, because even fighters cannot get G10, right? And the big airplanes, of course, with G10 would just disintegrate at that location. So you would say that something is wrong. And then we are looking into this for many years, not only us. Recently, in Denmark, Danish expert Glenn Jorgensen made calculations, and this information is on the YouTube. His lecture was in Denmark, done in January. So you can see that what he's, in fact, he had the same motivation as I had, which means I wanted to prove that the original report is correct. And I just wanted to verify that with my methodology, and he also wanted to do that. And when he put his time and I put my time, we found that the report has no sense whatsoever. So what he's saying that okay, this is the location of the birch, and let's say the airplane lost 6 meters of the wing, and the one wing is 18 meters or 19 meters long. So 6 meters is about 1/3 of the wing, and that part of the wing is here. It is flying from the left somehow to the right of the center of mass of the airplane, and landed in the bushes and trees, and is visible through the satellite picture. But he found also that other parts from this wing are in shrapnel shapes here, and this is the location of the first contact of the airplane with the ground. So the question is, what could happen that the other 1/3 of the wing is in shrapnel form somewhere in the middle, when the airplane was definitely flying, because this is the mark when the airplane is touching the ground. So he also looked at the black boxes, and he found that you can see in that location, a little bit before first and second debris, you can have 2 dips of the G-force, which could be related to loss of this wing, and therefore loss of the lift force. We also found, through analysis of the satellite pictures, because I have to say that until now it is almost 4 years no person from outside of Russia has any access to the debris of this airplane. Although it was Polish governmental airplane, but it is still in Smolensk. All the black boxes are still in Moscow, and nobody from outside of Russia has any access to the originals and can get anything out of it. There are some parts smuggled by people, which happens, but officially they are not available. So what we found that on the 11th of April, this is the part of the stabilizer, and this is the location of the first touch. This is the first touch of the airplane. You can see the grooves that was done by some parts of the airplane in the ground. And this part from 11 to 12 of April was moved by some unknown forces by 50 meters. So we asked Russian what has happened, and they first denied that no, this was the original location, but when we presented pictures from the satellite, they eventually agreed, and they said, yeah, it was, people were trying to steal those parts, and militia stopped them, and they dropped it here. So we asked, so why in the official report the new location is marked, not the original mark? And this they didn't answer already, because they said that this is a rude question. So they don't answer to rude questions. You know, to be limited by not having the access to the parts, we can rely on physics and mathematics. So what I did, I made the analysis using CFD technique and allowed this 6 meters of the wing to accelerate to a particular location in the air, and then I let it go and found so-called free path of the falling down this wing, because it was interesting to me how it is possible that the wing that was broken on the left side can fly to the right side. Is it possible physically? And I found that yes, it is possible. You can see this is three-dimensional path, and this is the location in the, this is the center of mass location. So it goes from the location on the left and going to the right, because the flight is this way. However, in order to reach this distance, you require certain height of the airplane, and that height of the airplane is about 30 meters above the ground. So then another scientist found that the TAWS measurements from this airplane was sent to be read in the United States, and we have access. This was one data point that we had direct access, and that TAWS gave different vertical trajectory than Russian showed, and again I'm showing this original Russian trajectory that was supposed to be 5 meters near the ground, but TAWS shows that the airplane never touched never hit this tree at all. And it was increasing the height, so the pilots said that we are go around, we are not landing, and they started to execute this go around decision. However, something happened later on that disintegrated the airplane in the air. Again, coming back to Jorgensen, it is interesting because his analysis using the aerodynamics is able to go back from the location of the first mark and find the trajectory, and he independently confirmed that TAWS measurement is correct. So in other words, if the airplane would be at that location, the airplane would not be able to reach the final destination itself. In order to get there, two things must happen. First of all, the airplane must be higher, and this was also compared by Dr. Kowaleczko who did independent calculations, and from his calculation there's 11.3 meters above the ground, which means a way different than 5 meters or 6 meters than that was stated originally, which agrees, by the way, with Tufts measurement. And also, Jorgensen says that in order to make that sharp left turn, you have to lose 2/3 of the wing. So indeed, you cannot just lose 1/3 of the wing, but you have to lose 2/3, which you can see debris are laying before the location of the contact with the ground. So all of that started to agree, no matter who did the calculation, either me or Akron, or Jorgensen in Denmark, or Dr. Dabaczyk in Baltimore. Everything agrees. However, nothing agrees with the official report that was presented to the world. So again, you can study more the available pictures from the satellite. Right now you can buy satellite pictures for a couple of $100. Anybody you can buy, and from commercial satellites, and you can see the satellite picture in April 2010. This is still spring, and then in June 2010. And interesting, this is the locations of called Tufts 38. This is the location where the airplane turned sharply left. First of all, this Tufts 38 was hidden in the official report. You cannot find it. You can download the report from internet, and you can find that this Tufts 38 is not there. However, if you are smart in computers and you take the PDF, you can open it, okay, because it was put a green square on top of Tufts 38 because they didn't like it, because the Tufts 38 not only shows that something over there happened, but that the plane flew straight. And if it flew straight, it means it couldn't lose the wing at the birch tree. It must be somewhere else. So that agrees with the Dr. Szladziński, who is expert in explosives, and he's the alumni of the airplane department of the Polish Warsaw Technical University, that has to be explosive in the wing that caused the middle part to deteriorate to the pieces, and therefore that 1/3 was just fly away due to the being not connected anymore to the airplane. And that happened for most likely in this location of Tufts 38. This is why it was hidden in the official report. Not only it was hidden, but also Russian did some work over there. They cut all the trees and all the bushes and removed about 2 meters of ground from that location. You can see from satellite picture. And again, we asked them, why did you do that? They said, well, because we didn't want next airplane to hit those trees and have another crash. So we asked, okay, but you left all these trees here, and they can be, so they said it is a rude question and they are not going to answer. But interesting also is that you can see here, this is the location of that birch tree, and according to the Russian report, this airplane is supposed to be here 2 meters or maybe 1 meter above the ground. So you can imagine that all these bushes and trees should be shaved, okay? It should not be there, but they are there in June, so obviously this is not enough time to grow again the tree. So that also confirms that the so-called birch tree is not the cause of the crash. So coming back to my methodology, you know, as engineer, I can build a model, and so this is a model of Tupolev 154. You have some measurements you can see the yellow trunk of the tree according to the official report, which is the input data, right? I also had to give the properties of the material, so Professor Cieszewski from the University of Georgia, he received part of this tree from Smolensk, and he tested it, and he found that indeed this is a regular birch tree, it's not anything stronger than any other birch tree. And in fact it's weaker because it is growing in the very wet area, and therefore it has a lot of water inside of itself. And I was able to put together the properties and the dimensions of this tree. You can see how many stems, nodes are in the area of crash, and every node is the weakness of the tree. So some of the experts from Canada said that this tree in fact is so weak that at that velocity, if a person would hit the tree, it will break. You don't need the airplane. But anyway, you can see the tree itself, how it is broken and why it was given the reason that this massive airplane lost its wing on this tree because it is broken. So what I did as an engineer and scientist can do, I bought some of the birch tree and I tested and I created a model, orthotropic model in this case, of course, and you can see that before my test I used linear model which gave the properties that I took from the literature, but then when I tested I saw that this material is more non-linear, and I used material 143, which is part of the newer non-linear material model available for the trees. Independently, Professor Boccieri in California did use the same material model 143 for testing of this experiment. You can see Constellation airplane, which is much older. This test was done in '65, and two poles, electric poles, are cut by the wing of this airplane. So the airplane, incidentally, is much lighter. It's half of the weight of the Tupolev, and therefore, as anybody that design airplanes, you know that you design wings according to the velocity of the airplane and its weight. So if your objective is to have an airplane that is flying much slower, which was in the case of Lucky Constellation, and much lighter, then the wing must be much lighter and weaker as well. In fact, it doesn't have, it has only two spars, front and back, and has the truss instead of ribs. So it's very light structure, and indeed, despite of the fact that this wing is much weaker, both of those poles were cut without any problem. As you can see, debris flying through that wing. Of course, this experiment was not designed to produce data for a crash of the airplane 30 years later, but or 40 or 50 years later, but it was done to analyze the spillage of the fuel. So they put more obstacles, the ground obstacles and big stones to rip off this wing to spill the fuel, to measure the fuel. And the report of this test is in the internet, Boccieri, you can look into Boccieri's. And he used the same methodology as I did. So although we don't know each other personally, but we use the same methodology because it is available. Now for the aluminum, we use first, bilinear material model. We use Johnson-Cook, which is strain rate dependent model, and recently we use this tabulated model, which is the most accurate that I already shown before here. So now, what is interesting that this test that I mentioned proves that this material is very plastic. But if you look into the field of debris, you have thousands. In fact, we got a report recently done by archaeologists that they measured, they found 30,000 of debris in certain area, not the full area. And debris are already found before this birch tree. So how you can find the debris of from the airplane before first contact with any tree, and also from the location of the tree all the way, it is rain of parts, as I showed you, this wing part, the second two-thirds of the part, and the debris at the location are shown here through this satellite picture. Well, Dr. Śledziński says that the more debris you can get, the higher energy is involved during the damage. So we calculated, of course, and due to the fact that the airplane was flying 80 meters per second, which is 270 kilometers per hour, which is not high velocity for the airplane, it landed from only 30 meters. The energy is not sufficient to disintegrate the airplane to small pieces of that nature unless it was explosive. So the conclusion was that there must be explosive involved, and also, as I mentioned, some of the parts were smuggled out of Russia. They don't let us have, but somebody brave enough brought this piece from the wing, and you can see the typical damage from the pressure inside of the wing. You can see ripped off the rivets and smoked internal part of the shiny part of the wing. So this is a proof that there was explosion in the wing. Again, if you look into the stress strain of different models that we use, like Johnson-Cook or bilinear, or this tabulated together with the material model used for the wood, generic orthotropic model or material 143, but if you need to squash this to this level to show the same vertical scale, you can see how weak the tree is in comparison with aluminum. I don't know if you saw, and I hope you saw, the airplanes that hit the World Trade Center, the September 11, during the terrorist attack, and the airplane went inside of the building. The outside of the World Trade Center, there are steel columns, so the aluminum was able to cut through the steel columns, and that paper is written by Tomasz Wierzbicki and available from MIT and available on the internet, so you can read how it is possible that aluminum, which is 1/3 of the strength of the steel, can cut at certain velocity the steel columns. So of course, if the aluminum can cut steel columns, which is 3 times stronger than aluminum, why there's any problem to cut the tree? This is the comparison in one scale of tabulated model and birch tree. So again, coming back to our model, we use structure of the Tupolev 154, but we didn't use so-called stringers because I wanted to have my wing weaker. To be sure, to be more conservative, I wanted to have my wing weaker, and I use 3 stronger, no knots, about 4 times stronger than really it is. Because I don't trust the initial condition data, then I use so-called parametric conditions, initial conditions to change the velocity vectors from 77 to 80 meters per second horizontal, from 0 to 19 meters per second vertical. With the known mass of the airplane, the batch density I changed from 700 to 1000 kilogram per meter cube, and I changed the location of the contact between birch and the wing, and different for all of that for different horizontal pitch and roll angles. as shown in here. My colleague from the University of Akron, Dr. Jack Brown, he is expert in aerodynamics. He used ANSYS CFX and calculated aerodynamic pressures, so we put those pressures on top of our loading conditions, and therefore we can show the simulations, how the computer predicts what would happen if this airplane would hit that birch tree. Again, assuming that I follow the official report. So what you can see that in each case, for every orientation of the airplane, basically the front edge is damaged, but then the birch is cut by the wing, and the airplane is flying away very quickly. The whole event takes 2/100ths of a second. Okay, flight is 80 meters per second, so within 1 second the airplane goes 80 meters, right? So the contact with the birch before it is broken to pieces is just 2/100ths of a second. It's very quick, very dynamic situation. So you can see in every case, for every model, some of them are more linear, more non-linear, but you have the same effect. The birch tree is broken, and it falls, the upper part, due to dynamics, has to fall in the direction of the flight. Okay, there's no other way. This was also proven by Bacelli experiment. What is interesting that in Smolensk, the birch is laying perpendicular to the direction of the flight, which cannot be explained physically at all. I look from the bottom of the surface of the wing, and I can see that there's no contact between the lower part of the tree, again because it's so much inertia involved and dynamic event that the wing has to just cut by, has to cut this tree and go away. So, but always the front edge is damaged. So no matter what, the front edge is damaged. I did calculations for different thicknesses of spars, different thicknesses of ribs and skin of the airplane, and in every scenario I calculated, I had the same results, that the airplane, if it would hit really this tree, the tree would be cut in half, should fall down in the direction of the flight of the airplane, but in fact it is not the case. If you look at the debris and put together and reconstruct the airplane wing, this is the part that was flying away, but the front edge is not damaged. This is supposed to be damaged part when the tree is supposed to cut through the airplane. But the slots, so-called, you can see they are not damaged in that location. However, you have a big hole here. So how you can rip the big hole in the middle of the wing without damaging the front edge? Definitely not by tree, but yes, you can do it if you have explosion in this area. Then this part is just flying away because it's not connected to anything. Professor Cieszewski also recently bought some of the satellite pictures again, and he found the location of that tree with respect to other objects. This is the magnification of the tree from the 12th of April and 11th of April that we know it's broken. So through the low resolution, unfortunately, the satellite picture, you can see the white spot of the trunk of the birch tree, which is white. And in January 26, this tree was standing. He's the forester, he's the expert to read from the satellite pictures. He did it together with his colleagues in University of Georgia, and all 5 professors agreed that this is a standing tree and this is broken tree. So here you don't see any white because the trunk looking from, the branches looking from the top, the trunk you don't see it, is all dark. So then he found the picture from April 5. and he asked audience, is that same location from April 5 similar to these pictures or similar to this? What is your vote? Who believes that this is the same as this two? Raise your hand. Okay, who believes that this is the same as this? Raise your hand. Okay, you're right, okay? So it means, the conclusion is that on April 5, which is 5 days before the crash, the tree is broken. Of course, the official Russian says, no, this picture is the same as this. So, you are wrong. Sorry. Well, I also did some simulations of fuselage that is dropping down upside down. So you can see red wall, floor of the fuselage, and no matter how I drop this fuselage with the angle of rotation or without, either one wall or the other wall and ceiling is broken under the floor. But people from Sandia National Lab did the same calculations or calculation or behavior of fuselage. What will happen, how this fuselage will behave if you apply explosives inside. So this is shown, the results in 2008 by Sandia National Lab, and the pressure from explosive rips the fuselage and opens this outside. So if you have explosion in the air, you rip off the fuselage axially, and the ceiling and wall goes on both sides of the airplane. So this is one of the debris of the fuselage in the Smolensk. You can see the floor, this is the floor, this is the bottom of the airplane, this is one wall, this is another wall and ceiling. So that, to me, represents the situation that was done by Sandia National Lab, not the one that I did it before when I crashed this particular fuselage without explosives. So I did explosives as well, upside down, and indeed you can see that the ceiling and wall goes on one side and the other wall goes on the other side. And then you have the situation as captured by the photographs of the debris in Smolensk. The last analysis that I did was, okay, I'm a stubborn person, so I wanted to do all the calculation based on the official report that says that the airplane lost on the wing, and its whole mass hit the soft ground because there was very soft, wet floor without any stones and any bricks and any rocks. So my simulations of the whole mass of the airplane, depending on the angle of heat with the 80 meters per second, produces the crater. Okay. Again, you know, you are talking about 78 tons of mass hitting 80 meters per second in the soft ground. It's normal that you can expect a crater. So the crater should be about 1-2 meters deep, and you know, the width should be bigger than the width of the fuselage, or maybe even bigger than fuselage and wings, and it should be very long. Depending on the orientation, it could be very long, more than 100 meters long. I did this with the airplane downing with the wheels down, and later on it was shown experiment using Boeing 727, and Boeing 727 is very similar to Tupolev. You can see both dimensions and weights in the table shown over here. So any accidents using Boeing 727 are very interesting. This is one of the report of the JFK crash when the airplane Boeing 727 hit the lighting towers in 1975 with the left wing. you can see that the airplane contacted the top of the number 7 approach light tower at the elevation of 27 feet above the mean low water level and 2,400 feet from the threshold of the runway 22L. The aircraft continued and struck towers 8 and 9. The aircraft left wing was damaged severely by impact with these towers. The outboard section was severed. The aircraft then rolled into steep left bank, well in excess of 90 degrees. It contacted the ground and the fuselage struck 5 other towers. The aircraft then continued to street where it came to rest. The approach light tower and large boulders along the latter portion of the path caused the fuselage to collapse and disintegrate. A fire had erupted after the left wing failed. Okay? So it is kind of similar scenario and that was presented by Russians. However, you can read also from the newspapers that in this plane, despite of the fact that it hit those multiple towers, some people survived. 109 of 122 plane feared death. So about 11 people survived, including 2 children. You can see how these towers look. These are not just a pole, easy to cut. These are steel structures, like truss structures, and one of them is completely cut in half by that wing of this airplane. You can see the boulders over here and how big boulders disintegrated this airplane, but seats of the airplane are still intact. Well, if you compare with the Tupolev F-15-4, there was no boulders, there was no tower, there was just one tree, and all the airplane is disintegrated to pieces, including seats. There are no one seat that is intact. This is another experiment done by Boeing 727, done in 2012, where it was equipped with dummies and sensors without any human being inside, and the objective was to cause the explosion of this airplane. The airplane hits with the higher velocity, vertical velocity than the Tupolev, and breaks to 3 pieces. Of course, if you are a human being and you are flying in business class, I'm sorry, you are dead. But if you would be sitting in the middle or aft part of the airplane, you will survive. Despite of the fact that this was very bad crash, you will survive. The accelerations are such that you will have some broken ribs, but you will survive. Well, that experiment validated my simulations, which was done before, and my simulation also broke into 3 pieces. So I could now make a simulation with upside down configuration, and I found that accelerations inside of this airplane are lower if it hits upside down than if it would hit with the regular way. The reason is that it has this tail and engines, and those tails and engines, each engine is 9,000 kilograms. It's a lot of metal, and that absorbs the energy before the fuselage is in contact, the aft part of the fuselage is in contact with the ground. So again, people in the front will die, but the aft people should survive. Unfortunately, in Tupolev F-154, everybody died. Not only died, but many people were basically found in pieces. One of the family member told me that she received in a coffin on the hand of her husband. We don't know where is the rest. So we made simulations. You can see how this crater and the disintegration of the airplane happens if it is flying upside down. These are all very expensive simulations. It takes months of calculations on a good computer to get results because of the explicit nature of the calculations. What is interesting that in this case we found that at least one wing should survive. There's no reason that both wings would be damaged. You know, one was damaged because of the tree, but why the other is damaged, there's no reason whatsoever. Now, in the official report, it says that the airplane really hit not upside down completely, but kind of on the left wing, on the broken wing. So, in fact, this is even better, giving more survival chances for the airplane. And again, we can show the results of Sioux City, Iowa case, where the airplane hit the ground on the wing, rotated many times, disintegrated to pieces, landed eventually upside down, and you can see people walking outside from the middle part of the fuselage, although fuselage is disintegrated into big chunks of the airplane. Again, you can see seats are in good shape, okay? And if people are dead, they are also dead, but they look like people, not like piece of meat. Some cases where the airplane landed upside down, in this case it was Kyrgyzstan. Apparently Russian likes to land upside down, and in this case you have all survived, 31 injured. This is the same airplane, Tupolev 154, landed in the forest, disintegrated into 3 pieces again, cut through forest. Didn't lose any wing, but just sheared hundreds of trees without any problem. And people get outside. It was in the moment of this crash, 83 people were injured, all survived. Later on, 2 people died in the hospital. Well, this is what has left from this airplane, which you can see at the tarmac of the Smolensk airport. So this is the left wing, but look at the right wing. It's also damaged completely. Look at the fuselage. The wing, the tail was found before the contact of the airplane. So all of that can be summarized. Okay, it's one more picture to show. This is this birch, and before birch are the parts of this airplane, and you can see all these parts that are shown here along the way of flight of the airplane. This is the part that is hanging before that birch. You can see the distance between birch before. So how that thing would fly after hitting the birch backwards, I cannot figure it out. Basically, the conclusions can be that a separation of 1/3 of the wing could not cause by the impact with the birch tree. Most probably separation of a fragment of the wing was caused by explosion in the air. Lack of visible crater at the crash scene, a large field of debris indicate that the airplane disintegrated in the mid-air. And then those parts, not as a one mass, but as a rain of parts, fell down, therefore they didn't create any crater. Open walls outside of the fuselage indicate mid-air explosion. The unprecedented degree of damage and the large number of shrapnels indicate high energy mid-air explosion. Without the mid-air explosion, most of the passengers in the center and in the aft section of the airplane should survive any crash from 30 to 40 meters into the soft soil. Official Russian report attributes death of the passengers to 100 G acceleration. Such acceleration could be explained by explosion in the fuselage, shockwave produced by explosion, and direct impact of the passengers with the ground at 80 meters per second without any protection of the fuselage. And this is all. Thank you.
Thank you, Professor. We'll just take a couple of questions if anybody's got any questions there in the audience. Anybody have a question there? The one question I would like to ask, just very simply, is I know with regard to Boeing 727s, there are designed production breaks within the fuselage which will cause it to split into three. I just wonder, does the Tupolev have a similar sort of structure in terms of the way it's designed?
Yeah, Tupolev is much stronger. It has 3 spars, not 2 spars. The reason is that technology in Russia is not as precise as it is in the Western countries, and therefore they produced first the same with 2 spars, but they found that they have too much deformation of the wing, and they equipped the 3rd spar into the wing of the airplane. So it's about 30% stronger.
Great, thank you. Any questions there from anybody? If there isn't, I'd just like to call on Tom Corrigan for a second just to say a few words, and while he's getting his way up here, I'd just like to remind anybody who's in the Royal Aeronautical Society or who's not in the Royal Aeronautical Society, there is a talk on the beach launching of gliders from Kerry beaches and basically mountain ridge soaring on Wednesday night in Wynn's Hotel at 7:30. You don't have to be a member to attend, it's free, and it's worth coming just to hear how people in our industry and in the sport end of our industry like to do what they do. So I just call on Tom now. Thank you.
Thank you very much, Paul. First of all, can I say, to echo, I should say, Paul's welcome to Professor, to the Royal Aeronautical Society, and to the Polish discussion group. DIT and the Royal Aeronautical Society go back many, many years. And in our history, back in 2011, when this building was actually built, we did have lectures on aircraft construction. So we're embedded in our aviation here down through the years. I have to say that I intended to take notes and be able to respond to things that were said, but I got engrossed in your lecture so much that I put the pen down and just said, I'm going to listen to this. I was particularly interested in the development of the materials, of course, and how they're now implemented. And one question that I should have responded to Paul's question was, how repairable are those materials now? No problem?
Yeah, we have a big problem with repair of composites. Yes, this is still ongoing research, and any students who are working here in Ireland can pick up that question. Obviously, we have some glues, and we can. One of the colleagues here pointed out to has very strong glue, so we can use the composite by basically retrofitting and adding to it by using strong adhesives. We don't know how they age, how they behave in the conditions of the flight. There's a lot of questions. Fortunately, so far we have no damage to the composite Airbus or composite Boeing yet, but these problems will come, so it is a good moment to start thinking about that for students. You can be a very look after expert if you have any experience in repairing of composites in aircraft. Thank you.
Thank you. Thank you, Professor. When you moved on to your crash investigation, as you discussed it and as you talked about it, it took me back to a situation where we had an air crash back in the late 1960s, where we had a Viscount, Aer Lingus had a Viscount that crashed off Tuscarora, and we were ably assisted by our colleagues across the water. And it also left that kind of doubt as to why did they assist, what really happened, and what was the true outcome. Perhaps if we had had your models back then, we could have come to maybe a different conclusion, or at least challenged the conclusion that actually did arrive. So with that, I won't hold anybody else up again. Thank you, Professor, thank you, Paul, and thank you to the Polish community, and ladies and gentlemen, thank you for your attention this morning. Thank you.